Hello GATE aspirants, welcome to part 15 of GATE quantum mechanics series. Question number 13. The wave function of a particle in an infinite one-dimensional potential well at time t is given, where psi1, psi2 and psi3 are the normalized ground state, the normalized first excited state and normalized second excited state respectively. E1, E2 and E3 are the energy energies corresponding to psi1, psi2 and psi3 respectively. The expectation value of the energy of the particle in the state psi is. Expectation value of energy is equal to summation over Ci square EI upon summation over Ci square. Here Ci square first is root 2 by 3, so 2 by 3 into we have E1 plus 1 by 6 E2 plus 1 by 6 E3 upon 2 by 3 plus 1 by 6 plus 1 by 6, which is equal to 1. So this is equal to 2 by 3 into E1 plus 1 by 6. Now E2 is 4 times E1. So this will be equal to 4 into E1 because it will be n square E. So 4 E1 plus 1 by 6 into E3 is 3 square into E1. So 9 into E1. So this is equal to 2 by 3 plus 2 by 3 plus this is 3 by 2 into E1, which is equal to 17 by 6 E1. So here option A is correct. Next question. The particle is subjected to a potential V of x. It is infinity when x is less than 0. So that means this wave function has to be equal to 0 when it is tending to 0. So at x is equal to 0, it should be 0. So this option is wrong definitely. Next, V0 is V0 in range A to B and it is 0 L square. So if wave function is 0, then that means it will be oscillatory. So that means if V of x is 0, then that means it will be something of this kind, oscillatory. And in this region A to B, it should be exponentially decaying. So let us see where it is matching. So it should be exponentially decaying in A to B and otherwise oscillating. So option B is correct. Next question. Following trial wave functions phi1 and phi2 are used to get variational estimate of the ground state energy of the helium atom. Z dash and G are the variational parameters. R1, R2 are the position vectors of the electrons. Let E0 be the exact ground state energy of the helium atom. E1 and E2 are the variational estimates of the ground state energy of the helium atom corresponding to phi1 and phi2 respectively. Which one of the following options is true? Now energy of the trial wave function will be always greater than the exact energy. Now exact energy is E0. So this E1, it has to be greater than or equal to E0, and E2, this also has to be greater than or equal to E0. So first of all, let's check that. So E0 should be smaller. So this is wrong. This is correct. This is wrong. Then again here it is wrong. And in option D, E1 is greater than or equal to E0, E2 is greater than or equal to E0. So option D is correct. Just check that the actual energy will be less than the trial wave function energy. So option D is correct. Next question. The wave function of a particle is given by this form where alpha and beta are real constants. In which of the following potentials V of x the particle is moving? Now this psi is of this form, e raised to minus I alpha x e raised to minus beta. Now e raised to minus I x, this form is for plane wave function. This means that this V of x should be either 0 or it will be constant. That means option C is correct. or you can use Schrodinger wave function and solve it. So we have minus h cut square twice m d2 psi by dx square plus v of x psi is equal to e of psi. Now psi is given. Now what will be psi of x? Psi dash of x? It will be equal to e raised to minus I alpha x plus beta into I alpha. So let us type the double derivative will be, it will be into minus I alpha square. So I alpha square, which is equal to I square is minus 1. So this is minus alpha square psi. So this is equal to minus h cut square twice m minus alpha square psi plus v of x into psi e of x, e of psi. So this is equal to h cut square alpha square twice m plus v of x is equal to e. Now energy is h cut square alpha square by twice m. That means this v has to be equal to 0. So potential is equal to 0. Next question. A particle of mass m is moving in this potential. Figures P, Q, R and S show different combinations of the values of omega naught and V naught. Energies are eigenenergies of the jth level for the potentials shown in the figure P, Q, R and S respectively. Which of the following statement is true? Now this is, from the figure we can see that it is half quantum harmonic oscillator. So this is half quantum harmonic oscillator and its energy is equal to J plus half into h cut omega plus V naught, where J is taking values 1, 3, 5 and so on. Now let us calculate energies in each case for P, Q, R and S. Now for figure P, this E naught P, this will be equal to, for the first case, that means J will be equal to 1. So 1 plus half is 3 by 2. So this will be 3 by 2 h cut into omega is 12. So into 12 plus what is corresponding V naught? Potential is not there. So 0. So this is equal to 18 h cut. Now E naught for Q. Here we have again energy. So here it is considered value of J because this is in E naught. So first is J is equal to 1. So that is equal to 3 by 2 h cut and corresponding omega is 12 here. Plus we have potential which is 3 h cut. So this is 18 plus 3 which is 21 h cut. Now next is E naught R. I am calculating only those which are here in the options. So E naught R, this is equal to E naught, so this is 3 by 2 h cut and corresponding omega is 4 plus V is 4 h cut. So this will be equal to 10 h cut. Next E naught S, again 3 by 2 h cut and for S omega is 14 plus corresponding V naught is 0. So this is equal to 21 h cut. And one more thing is here E1R. So E1R, that means J, value of J will be 3 now. So 3 plus half which is 7 by 2 h cut and omega is E naught R, omega is 4 plus 4 h cut and this is equal to 18 h cut. Now we have to see. Now first option E naught P is equal to E naught Q, wrong. Option B, E naught Q is equal to E naught S. Yeah, so this is true. Next we have E naught P is equal to E1R. E naught P is equal to E1R. Yes, it is correct. And E naught R is not equal to E naught Q. Yeah, this is also correct. So here option B, C and D are correct. Next question. The non-relativistic Hamiltonian for a single electron atom is H0 is equal to P square by twice M minus V of R, where V of R is the Coulomb potential and M is the mass of the electron. Considering the spin orbit interaction term added to H0, which of the following statement is and R are true? Now here we can see this H dash is proportional to L dot S. So we have to find out if it commutes with L square, if it commutes with LZ, SZ, and so on. So for first option, if we consider L square and L bar dot S bar, then this is equal to L square and L dot S, it can be written as, this is L square and L dot S can be written as J square minus L square minus S square. Upon 2 is also there, but that doesn't affect the commutation relation. And then this is equal to 0 because it commutes with all. So this is 0. So yes, option A is correct. H dash commutes with L square. Now for the second option, we have LZ here. So we have here LZ and L dot S will be Lx Sx plus Ly Sy plus Lz Sz. Now this will be equal to, now we have to open this bracket, separate it all out and then solve it. Now Lz will not depend on Lx Lz and Sx Sy, but it will commute with this Lz Sz, and if you solve it, you'll get I h cut Lz Sx minus I h cut Lx Sy, and this is not equal to 0. So it is not commuting with this Lz and Sz. Similar case will be for Sz, so it will not commute. Now, next is, for a given value of principal quantum number n and orbital angular momentum quantum number L, there are 2 into 2L plus 1 degenerate eigenstates of H0. Now, if you consider any L, then ML takes values from minus L to L. So it does take 2L plus 1 values. And again, S takes values plus and minus half. So that means degeneracy will be from this S 2 and from this ML it will be 2L plus 1. So yes, it will split into this many degenerate states. So option C is correct. And option D, H0 L square S square Lz Sz have a set of simultaneous eigenstates. Now all these operators, they commute with each other. So they do have common set of eigenstates. So option D is also correct. Next question. A particle of mass m in an infinite potential well of width A is subjected to a perturbation V dash is equal to H0 square upon 40 Ma square, shown in the figure, where H is the Planck's constant and this is part is perturbation part. The first order energy shift of the fourth energy eigenstate due to this perturbation is. Now what will be fourth state, psi 4? This is equal to under root 2 by A, and then we have function sine and 4 pi x by A, and this is H dash. So psi 4, fourth order correction will be psi 4 H dash psi 4, which is equal to this root 2 by A. So we have 2 by A here, integration sine square 4 pi A by 4 pi x by A into this V dash. V dash is H square. Oh, it is not H cut. It is H square upon 40 Ma square into dx. And this integration is from this part only. So this is 3 by 4a and this is a. So this is 3a by 4 to e. So this is equal to, we have this constants outside, 2h cut square upon 40 ma cube now. And integration is from 3a by 4 to a, and the sine square function can be written as 1 by 2 minus cos of 8 pi x by a, this whole thing, into 1 by 2 into dx. So this is equal to h square upon 20 ma cube. Integration of 1 by 2 is x by 2 minus, this is 1 by 2 into integration of cos is sine 8 pi x by a into 8 pi by a, and limits are 3a by 4 to a. This is equal to h square upon 20 ma cube, and here we have a by 2 minus 3a by 4 by 2, so 3a by 8 minus, if we put a here, then this will be sine 8 pi, which is equal to 0, and if we put 3a by 4 here, then also it will be sine n pi type of function, which is equal to 0, so it will be 0. So this is equal to h square upon 20 ma cube into, we have a by 2 minus 3a by 2, which is a by 8, and that is equal to h square upon 160 ma cube. So answer is n is equal to 160. And there is one more way to solve this. If you want to find out correction in nth, first order correction in nth state, then you can write this as E1n, that means first order correction in nth energy level, which is equal to strength of perturbation into length of perturbation. Upon length of wall. So here this will be equal to strength of perturbation is h square upon 40 ma square into length of perturbation is this only. So that is a by 4, and length of wall is a. So this is equal to h square upon 160 ma cube. Ma square, sorry. Here also it is square. So answer is 160, and answer given in the answer key is 160 to 160. Next question. An electron in the Coulomb field of a proton is in the following state of coherent superposition of orthonormal states psi and Lm. Psi is given. Let E1, E2 and E3 represent the first three energy levels of the system. A sequence of measurements is done on the same system at different times. Energy is measured first at time t1 and the outcome is E2. Then total angular momentum is measured at time t2 greater than t1, and finally energy is measured again at t3 greater than t2. The probability of finding the system in the state with energy E2 after the final measurement is p by 9. What is the value of p? Now here it is given that after first measurement outcome is E2. So H operated on psi is giving E2. And you will get so E2. So if it is giving E2, that means n will be 2, and where it is 2, here 210. So it will be 210. That means psi is equal to 210. Now if L square is operated, total angular momentum is operated on psi, that is if it is operated on 210, that will be L plus 1 h cut square into 210, which is equal to 2 h cut square 210. So this is 210, and now if h cut is operated on 210, then that will give E2 210. And here it is given that probability of getting E2 is, now here the thing is, this state is available only this state is available, E2, that is 210. So probability of getting this state is 1 only. You'll get this state only because that only that state is available now. And given is this probability is p by 9. That means p has to be 9 because final probability is 1. So answer is 9. Answer given in the answer key is 9 to 9. So these were all the questions from quantum mechanics part in GATE 2024 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.